¿Podés, Palo, ponerlo a pantalla completa?
Sí, pero se quedan solos. Así que bueno, queda confiar. Queda confiar.
Si no, porque si no tengo la tablet para transmitirlo ahí, que eso no pasa nada.
¿Querés probar?
Dale.
Mora, entre las dos vamos viendo el YouTube.
Dale, Lu.
Ok. Ah,
Che, tenemos, nada que ver, Marco y Palo, tenemos bi-weekly en un rato. Tipo con HQ, que yo se me había acumulado de
¿No
la
tuve
cabeza.
yo, ¿no tuve yo la semana pasada?
Es lo que yo me pregunto, pero apareció en el calendario igual hoy, así que no sé.
De vuelta se baja el uno y se conecta. Igual es a las 8:30, ¿no, Ani?
Sí.
Yo calculo que vamos a estar.
Che, ¿en YouTube ya se ve todo? O sea, ¿ya se está transmitiendo o por qué lo estoy viendo?
Sí. Sí, hace
Sí,
un
sí.
rato que estamos
No digas
en
nada
vivo.
comprometedor, que hay 10 personas viéndote, que somos nosotros básicamente.
Ah,
Anda muy a pedal, ¿no?
A ver, pasa.
Pasa que no puedo presentar. A ver, ahí.
¿Se ve
¿Ahí?
bien? Sí, se ve bien.
Ok.
Bueno,
Ok,
bien.
voy a poner
Gracias.
no molestar así, no llega nada. Creo que se unió alguien, ¿no?
Sí, ya hay un par de participantes.
Ah. Bueno, buenas tardes a quienes se están uniendo. Hola.
Hola, ¿cómo va?
Hola, buenas tardes.
Bien.
Buenas.
Vamos a esperar hasta las 5 a que se terminen de unir todos.
Buenas, ¿qué tal?
Hola.
Hola. So we're gonna be doing most of this in English because we want everyone, especially David, to understand what we're saying. So most of this is gonna be in English, but yeah, feel free to ask questions in any of the two languages.
Hey, David. Just for you to know, we are live streaming this on YouTube. So if anyone is seeing us on YouTube and wants to ask a question in Spanish, you can leave it there and we can translate it and send it to David. I mean,
Sorry, what?
no, you can continue.
Yeah, sorry. My iPad stopped presenting, so there we go. We're not waiting for any more people, are we?
We are all set to go.
No, we're good.
All right, so it's all of us. Welcome, everyone. We are super excited to have you here and to be here. This is the beginning of the 2025 edition of the Genesis program. You all probably know why you're here and what this is, but we are going to go over it a little bit anyway. And so this is a little overview of what we will be going over during the talk. We will first introduce nuclei. Then we're going to listen in on David's lecture about venture creation and identifying real problems and finding innovative solutions. Then we are going to use breakout rooms so you guys can meet your team license and meet each other. And yeah, we'll meet back in this general meet to have a closing statement. So to tell you a little bit about Nucleate, Nucleate is a nonprofit organization that was born in 2018 as a student-led initiative that was born in the Biotech Club of Harvard. And it quickly spread to other countries around the world, and it reached Argentina in 2022. And Nucleate's mission is to bridge the gap between academic trainees and the biotechnological industry. And we aim to train the next generation of biotech leaders. And I always say that this is very pretty, but what does it actually mean? And what it means is we basically are all volunteers who come together to organize very varied educational initiatives that are completely free of charge and that are designed for life sciences and business students who are interested in learning about venture creation and more specifically in entrepreneurship that is based on science. So all the science that we learn while at school, sorry about that. Palo, do you want to share your screen? Maybe that's better.
All right, just give me a second.
Because mine keeps going blank, but I can go back just for a second. Sorry about that. Sorry. So I was saying that Nucleate offers educational programs for people that are interested in learning about venture creation and science-based entrepreneurship. This is our team in Argentina. I'm Emilia. Paloma and Marco are the other two co-managing directors of Nuclear Argentina. And we have expanded our team to 15 volunteers this year. We're very happy about that. And we have students from all over the country because one of Nucleate's Argentina's main objectives was to keep a federal approach as to not have every initiative that we do isolated to Buenos Aires only. We want to reach as many students as possible all around the country. So it is important to us to also have volunteers from all around the country. Yeah.
I don't know if you want me to present now.
Yeah, let's switch just in case, because this is going
Okay.
to keep going dark. Okay. I'll stop now. There you go.
All right, you can see it, right?
Yeah, it's so low.
Yeah, we can see it.
Right. Well, and now I'm going to present the Genesis program. We're going to be together for 4 months in 6 modules. And first of all, we're going to be in the module 1 with principles of ideation and diligence. And we're going to meet our team members and their mentors. And we're going to have brainstorming sessions. Then we're going to be in the module 2 with intellectual property and most of all patent searching. There in the module 3, we're going to be in the risk management and the strategy with the risk reduction. And then module 4, selection of the technological application. Module 5, team building in biotech and venture financing. And finally, the storytelling and pitching with the final pitch that is going to be in person, where you can sell your idea to different investors in the Argentina ecosystem. And this year, we have 3 prompts for climate tech, health tech, and ag tech. And we're going to present the participants for each prompt. In the climate tech team, next-gen biochemicals, hacking resource production with biology. We have Melissa Dominguez, Santiago Calonge, María del Pilar Lence, and Lara Pugnaloni. In health tech, we have biotechnological innovations for enhanced quality of life and longevity. And we present Matteo Barbieri, Victoria Subel, Camila Feltrin, Anabel Diaz. And last, we have the AgTech team with molecular farming and synthetic biology, unlocking plants and microbes for commercial and agriculture innovation. With Jessica Céspedes Martínez, Germán Ariel Dalinger, Guadalupe Bernal Bustos, and Franco Maggi.
So today for our first lecture is joining us David. Thank you so much for joining us. And David is a PhD in biological engineering from MIT Media Lab, actually director of the MIT Media Lab community and biotechnology initiative. David is also the leader of the community biology movement and creator of the Bio Summit and co-founder of How to Grow Almost Anything. All of these are initiatives that are amazing, and I encourage you to join them and to know more about it. But I think that David can continue if ready.
Yeah, I'm ready. Let me share my slides. We tested this earlier, so hopefully this will work. Give me a moment. But it's so great to be here with you all. Thank you so much again, Marco, for inviting me. And it's a real pleasure to be here with everyone.
Thank you so much for joining.
Of course, my pleasure. Are you seeing some slides?
Yes.
Yeah, we can see it.
I'm gonna go full screen on the slides. Okay, are the slides full screen now?
Yes.
Yes.
Okay, so this is going to be, it's funny, I'm at MIT, so we're very used to presenting on Zoom. So I no longer can see your faces, so I'm going to talk to the computer. But you can see me okay, and you can see the slides okay?
Yeah, you can hear us.
I can hear you. Yeah, great. So
Yeah.
Okay.
I can't
Well-
see any of your faces anymore. So, but I would love for this to be conversational in a way as well. So please feel free to interrupt at any time. Marco, I will defer to you. Please do interrupt if anybody raises their hands or if there's a question in the chat or anything. Please stop me. Yeah, and I have a bunch of slides, and I can share some thoughts and ideas. And but please do interrupt me at any time, and I'll pause this a number of times as well, so we can have a little discussion. But
I encourage the Genesis participants to stop David and ask questions. This
Yeah,
is all about
please.
the program. Yeah.
Exactly. And and Marco, and I appreciate very much learning more about Nucleate and also the work that you all are doing and the innovation that you are all trying to engender and catalyze. And I thought what I could do today, I framed this talk as innovation at the edge. And the reason, again, I use this type of an idea, the Media Lab, which is the institution that I currently work at and I'm from, I think we've got a really rich history of developing different types of innovations, different technological innovations. And I think there's a really kind of key set of concepts about exploring the kind of edges of different types of research or technical domains, because so much of the exciting ideas and the exciting work happens at those edges. So I'll talk a little bit more about what I mean throughout this lecture. So again, I direct the Community Biotechnology Initiative at the Media Lab. Please feel free to reach out to me. I'm at David Sun Kong on all of the various social media platforms and also on LinkedIn. So please stay in touch. Would love to chat with you all more about anything I shared today, and also, again, excited about all of your innovation journeys and all of the projects that you're going to be working on as a part of this program. And as I mentioned, I work at the Media Lab, so please come and visit us in Cambridge at any time. It's a very, very special place to work. And I think it's also a really interesting sort of innovation factory. So many incredible ideas have come from the Media Lab and the research that happens there. And many of those ideas have turned into companies and have turned into really exciting commercial products out there in the world. And so there's around 30 or so different research groups at the lab. I think this idea of multidisciplinary research is a very common one now. The idea of kind of bringing different disciplines together and exploring innovation in those ways. And I would say, the Media Lab has, I think, a really interesting approach. So, I think everybody on this call, you are all engaging in biology and biotechnology and science and engineering in some way. But the Media Lab also explores very deeply art and design. And I think these are 4 domains of creativity that when we explore them together, again, there's a lot of really interesting and exciting innovation that can happen. And so there's a lot of research at the lab, of course, exploring different elements of innovations now in AI, both for learning and also for other applications, robotics and so on. At the Media Lab, we also explore music, textiles, human-computer interfaces, biomechatronics, synthetic neurobiology, so many different kind of spans of creativity from the molecular to physical systems to music and beyond. And so this leads me to this kind of deeper question that my group, the Community Biotechnology Initiative, we think a lot about, which is who gets to participate in science and technology. And so I bring up this idea again of innovation at the edge, and those edges have a lot to do with who ultimately has ideas and is empowered to contribute to a different type of scientific discipline or endeavor. So, for us, I think everyone on this call, again, all of us are engaged in the life sciences in some way. And so, I think all of you are very familiar with synthetic biology, so I won't go into the details of the kind of technical parts here. But, I think that there's a really kind of magical thing that happens when you take something like synthetic biology, which is normally a very, I would say, very privileged form of creative expression, right? For us to explore and innovate in biology, you need a lot of lab equipment, you need a lot of infrastructure. It's a very privileged kind of explorative endeavor. And for me, part of my background is technical and synthetic biology, but also in community organizing. And so I think a lot about how to bring biotechnology to very, very diverse communities all around the world, okay? And so this goes, again, to the edges, right? How do we take something like biotech, which can be, again, a very almost elite form of expression, but really bringing and inviting communities from all around the world to participate? And so this is a set of ideas, I think, that ties actually a lot into creativity and innovation. And so, diversity, it's funny, in the United States right now, diversity is a word. It's a word that people are actually very much under attack, which I think is a very interesting kind of phenomenon that's been evolving. But diversity, I think, is actually very critical for us to think about when we want to be highly innovative, right? And so there's actually a lot of very exciting social science that looks at diversity and within groups and links it to more innovation, for example, in solving problems and being able to make better predictions. And this is a landmark paper from my colleague, Karine Lakhani from the Harvard Business School. And they ran a series of studies looking at problem solving. And what they found was that this is a key line. The provision of a winning solution was positively related to increasing distance between the solver's field of technical expertise and the focal field of the problem. In other words, if you're trying to develop a solution to a problem in biology or biotechnology, it's actually better to find somebody that is as far away from biotechnology as possible. In other words, this sort of gets at a simple idea, which is, if you're around a lot of people that think very similarly and have very similar backgrounds, very similar experiences, then the idea of coming up with a truly disruptive idea is actually far lower, right? It's only through exploring, engaging with people from other creative backgrounds, other cultural backgrounds, other types of ways of thinking and looking at the world that you get the truly disruptive ideas. And we see this in the field of synthetic biology, which all of us are connected to. So this is a photograph of my dear friend and colleague, Drew Endy, when he was still at MIT. And for those of you that don't know, Drew actually was a civil engineer. Okay, so Drew was an engineer. He was not a biologist, trained as a biologist. And he was somebody that was thinking, why can't I apply engineering principles from domains like civil engineering, mechanical engineering, computer science, and electrical engineering, and apply those to biological systems. This is an extremely kind of exciting new set of ideas about 20 years ago now, in the early 2000s. And so, again, engineers thinking about biology and combining these seemingly disparate fields together to form what is now biological engineering. And, when I was at MIT doing an undergraduate, there actually was no biological engineering department at MIT. This is something that came about actually after my PhD had almost finished up at the Media Lab. And this is, me and Drew, just from a couple months ago, both older, a lot older guys now. But the fields, again, have really changed a lot. And I think this whole idea of being very inclusive, bringing very diverse voices into synthetic biology has been such a huge part of the future. And, again, the whole biotechnology industrial era has, of course, been going through its own gyrations. And, Ginkgo went public a number of years ago, a lot of big success. Now, a lot of challenges, but, it's been an exciting journey, I think. And I went to grad school with Jason and Reshma and Barry and Austin, known Tom also for many, many years. So, really great friends and colleagues. And it's been amazing seeing, how something like engineering could be brought into a discipline like biology and has really changed it and created a whole new global industry. So these ideas, I think, are really important when we think about innovation. And, again, for all of you thinking about your own projects, I think it's really wise to look at these different edges and other disciplines that might not be as obvious. And so one big part, I think, about bringing in this inclusivity and this diversity is around tools, right? So we talk a lot and think a lot in biotechnology about the lab, right? We've got, a lot of very physical equipment, so much infrastructure that's required to innovate. But what if we could lower those barriers of access and make innovation more accessible? And a big part of that is using tools. And so this is actually a funny phrase. This is actually from Drew, a number of years ago. He's talking about this idea that a computer is not a computer. And, what does he mean by that? Well, so this is a computer. This is an early IBM system that is a computation machine. And this was a mainframe computer that could calculate the trajectory of ballistic missiles. And, again, was used in a very specific set of applications. But this is also a computer, right? This is the very first Apple computer, one of the first very models. And what's different between these two computers, I don't know if anybody has an idea. There's a key adjective that separates these two these computation machines. This second machine is called a personal computer, right? That adjective, personal, is very important. It's the idea that computation actually can be for me and for you, not just for IBM or the Defense Department or people working in very kind of specialized domains. This is the idea that computation is actually for everyone, and all of us can innovate and work with computers. This is a funny image. You may think, why is David showing us a picture of paint? But paint also went through a really interesting set of innovations, right? The idea of painting is existing outside of a studio space or outside of a kind of more specialized elite circle was also a very innovative idea in the early 20th century. And so this idea of making standardized paints, which occurred, again, this is a photograph from 1911, changed a lot of key ideas about who could participate in painting and who could actually use paints. And all of a sudden, instead of only being able to do portraits inside of a studio or inside of a place, a well-resourced environment, you could bring paint outside, right? All of a sudden, you could paint at the beach. You could paint and think about who had access to paint, right? All of a sudden, instead of just painting, the royalty, you could go and paint workers. You could paint people in the fields, right? So all of a sudden, the idea of who can be painted, the representation of painting changed dramatically with a technical innovation around these standardized paint tubes. So even in my own work, I thought a lot about this for tools for synthetic biology. Okay, so in synthetic biology, there are all of these different types of systems and equipment that we use. And over the arc of my career, I've explored a lot of different types of tools and thought a lot about how we could increase the accessibility and let many, many people participate using more accessible tools. And so I'll go through this set of slides, and then I'll take a moment to pause for some questions. So one of the big areas in my own professional work and career has been around what's called lab on a chip or microfluidic technology. I'm guessing many of you are familiar with the idea of microfluidics, but for those that this may be a little bit new, we've used miniaturization and many other disciplines to a tremendous exponential impact and benefit, right? All of us now take for granted the fact that we can carry very powerful computers in our pockets, but all of this is enabled through miniaturization revolutions related to transistor technology, right? Early vacuum tubes were, very, very large systems that were miniaturized into transistors and then ultimately into integrated circuits. And now with semiconductor technologies, again, we have really ubiquitous computing. And similar types of innovations have been developed over the years with miniaturizing biological and chemical processes, in particular using a similar kind of unit or primitive, which is a valve, right? A valve in manipulating fluids has been a really critical feature going back to the Bronze Age, and of course, increasingly into microfluidics. And microfluidic technology typically involves micrometer to nanometer sized dimensions and volumes, right? So microliters and nanoliters. We're very familiar, I think, for microliters in a laboratory setting. Nanoliters tend to be like the volume, for example, of a printed period on a piece of paper. And this is an image of a human cell that is about a picoliter that's infected by bacteria that I think this is actually chlamydia. And each of those bacteria is a femtoliter, so I keep going down by orders of 1,000. And so microfluidic technology explores manipulation of fluids across those different scales. So these are all different images of different microfluidic devices on the bottom left-hand corner. These are microfluidic valves being actuated. These are different microfluidic bubble technologies that I've worked with over the years. Each one of these different glowing dots here represents an engineered organism that's expressing fluorescent bacteria. And so all of these different devices and these technologies have been really powerful, and you can use them in a lot of different ways. Again, all of you are familiar with DNA synthesis technology, I'm sure. And one of my earliest works in my doctoral thesis was applying microfluidics to miniaturizing gene synthesis, so the ability to fabricate and synthesize artificial computer-designed even gene constructs. And later on at MIT Lincoln Laboratory, worked on demonstrating the first miniaturization of genetic circuit assembly. So some of you are likely very familiar with cloning technologies, Gibson assembly, Golden Gate assembly. And this was part of a larger Nature Biotechnology paper where we built open source hardware and built the first synthetic genetic circuits. And we've also applied this to synthetic protein synthesis. So again, each one of these different spots on this chip here is a different DNA design. And using microfluidics, you can combine in vitro transcription translation mix or cell lysates, mix those together with those DNA parts, and then actually test and synthesize different types of DNA parts on a DNA design. So this is another representation of that. And then this is showing the enzymatic activity, the performance data for each one of those different circuits. And this is applied to the design of enzymes that are called organophosphate hydrolases. So these are enzymes that can break down toxins in the environment. And you can prototype each one of those different reactors as a different protein design. And based on the fluorescence, you can have a sense of the performance of the enzymatic activity. I've also done work over the years on building what are called artificial guts. So many of you may be familiar with the microbiome and microbiome science and technology. And so one of the really kind of key enabling tools that would be really powerful would be devices where you could prototype and test different types of microbial communities that could be used for making different types of, for example, short-chain fatty acids, butyrate, other types of molecules that are important for cognition, exploring the gut-brain axis, and so on. And so, you know, over the years, part of my work as I've been developing these tools, again, has been thinking about how do we share these technologies? How do we make them more open source? How do we make them more accessible, more inclusive to enable these kind of diverse actors to come and participate in this work? And so one of the first classes that I taught at MIT was actually around using 3D printing technology, which at the time was an innovative way to actually make fluidic devices. And so, you know, again, a lot of these microfluidic devices that I've shown you, it requires very, very expensive infrastructure, right? You need fabrication facilities, clean rooms to even make them. And so this was almost 10 years ago now, but this was a very innovative set of ideas, being able to use commodity 3D printers that were only thousands of dollars in price to make DNA assembly technologies like 3D printed fluidics. And so this is a designer, Will Patrick, who had never been in a wet lab before, who designed many of these 3D printed structures. And we ended up publishing a paper together with the students from the class. And I'll share this story. You know, so a whole number of the folks actually in this photograph, you know, a number of them I'll highlight here. So this is Will Patrick, again, had never been in a wet lab before. Became the founder of his own company called Culture Biosciences, which was doing and still exists. Actually, Will exited that company. And this particular one was focused on making bioreactors, right? Many of you that are trying to make fermentation systems, you know, Will really, as a designer, explored and brought his synthetic biology innovation together with his design background to make bioreactors. And again, you know, and Julie Legault is another great story, also a designer, had never been in a wet lab before, and is now the founder of her own company called Amino Labs, which makes desktop biology labs for learning. And this is another great story where Julie and Will, both designers, no expertise in biology, now CEOs of their own biotech companies, just a couple of years after starting in synthetic biology, but critically bringing in their own creative practices from design and art into synthetic biology. Alec Nielsen, many of you may know, the founder of Asimov, which is a leading synthetic biology company working on genetic circuit design tools. And, you know, again, over the years have done this the same type of idea for making 3D printed artificial guts, again, bringing very, very diverse folks into synthetic biology and also continuing to publish papers and work along those lines. And again, thinking about infrastructure for sharing, right? If we want to be radically accessible, share our ideas, one big idea is using open source infrastructure. So we published this paper a number of years ago now on a website called Metafluidics. And the whole idea is that all of these all of these device designs for microfluidics, you can also share globally all around the world. You know, when I was doing my PhD thesis, it was very annoying. You know, you'd try to, you know, you'd see some amazing new microfluidic design, but you had no access to that actual design file, right? So I couldn't recreate that work. I couldn't build upon that work. And so Metafluidics was an attempt to enable folks to share their design so other people could remix and build upon existing innovations from folks all around the world. So again, really radically reducing those barriers to entry for microfluidics. In my group, we've also developed other types of tools that are very accessible. You know, again, we mentioned this idea, computer's not a computer, right? A personal computer is different from a mainframe computer. Well, an electroporator is not an electroporator. Again, many of you may be familiar with a DNA electroporation, which is a technology for introducing DNA into cells. And some of my students, led by Teja, made a low-cost electroporator I'll play a little video here. Okay, and then this is Teja doing some field tests with Zapor in India. And so, you know, all of these different kind of tools that I'm talking about, you know, again, they're a huge dimension is about accessibility, inclusivity, but a big part is also creativity. And so I'll tell you very briefly about a project I've worked on with a company at the Media Lab called Accenture. The Media Lab has a whole set of what are called member companies, and TO.org, they're a foundation from Switzerland. And we're making biological cements. And so this is a really neat project where you can combine a type of microorganism called S. pasteuri, which is capable of a process called microbially induced calcium carbonate precipitation. So if you mix S. pasteuri with other reagents like urea and some calcium carbonate sources, you can actually create a biological cement. And you can use a casting and molding process to make these. We were working on introducing a carbon capture capability as well into these materials. And one of our collaborators is Chris Voigt from Biological Engineering, and there's a PhD student that I co-advise with Chris called, her name is Ren Romlin, amazing PhD student, and also bringing in fungal materials. So Ren has been doing work on fungal synthetic biology and figuring out ways to engineer fungi so that they also can, for example, have color change or other types of genetically engineerable properties and characteristics. And working with TO.org, we've been thinking a lot about how do we then take these biocements and enable anybody around the world to build their own biocements. So could you take soils from Argentina, from Morocco, Senegal, and actually work with these different microorganisms and work locally and manufacture and create your own biocements? And again, from a tool building and accessibility perspective, a lot of the folks that I engaged with over the years are also designers and artists. And so we set to making a tool called BioAtelier. So this is a design tool for folks that are could be working in fields like design and biodesign, that may not have necessarily deep synthetic biology expertise, and enabling them to actually build and work and make their own biocements and living material artifacts. And so also we're engaging with artists around this as well. This is Claudia Conte, who we're excited to collaborate with, who's based in Switzerland. And so all of these different tools, I think, are ways to explore synthetic biology, but again, introducing many folks that may not be active participants in synthetic biology and lowering those barriers of access so that they can engage in innovation as well. So let me pause here. I'm going to stop sharing my slides for a moment, and I'll pause for any questions so far.
So, guys, anyone wants to ask a question? Meanwhile, David, I think we are all blown away. I wanted to ask you if you have, you have shown us that you have worked with a lot of different themes and a lot of different projects. So I wanted to ask you if you have any tips for facing or tackling a new problem, and how important you think is the diversity of the team tackling it. The teams are going to be facing these new themes and these prompts that we gave them, so they are starting to know a new area of knowledge.
Yeah. I think diversity in teams, again, is really important. Like, for all of the projects that I shared, I personally always work with a really interesting and diverse set of folks. There's a number of projects I actually have not mentioned, but traditionally I've worked with designers, wet lab biologists, computer scientists, social scientists, people doing collective intelligence, with many different projects, having multidisciplinary and very diverse technical and creative teams, I think is very exciting. It brings a lot of new energy, a lot of new ideas into solving the problems that you're interested in. I noticed some of the problems that you're thinking about, for example, climate technology, all very technical, important technical problems. But even if you think about And actually, there's a set of tools that, again, I can mention very briefly. I also been doing a bunch of climate technology or biodiversity related work. But even there, you might have a really powerful technical solution. It could be something like coral probiotics, which is something that I've actually worked a little bit on. And if you want to bring that into the world and actually bring that into the oceans to actually make a positive impact on, biodiversity or climate change, as an example, the technical solution alone is not sufficient, right? You actually need to do a lot of community engagement. You need to work with policy folks, so people in government, to get your technology out into the field and into the ocean in this case, right? So there's a whole other kind of talk that I give about which I frame as biotic design, which is both looking at the technical dimension, but also the social dimension of your technology, right? Because if you want your technology ultimately to have a social impact, you also need to be thinking about those parts beyond just the technical parts. So I mentioned that to say that, bringing in a lot of different folks that can help you think about your idea. Some of you, if you are, for example, thinking about climate work, how are you going to engage with policymakers? How are you going to engage with government if you actually want to have your technical solution become successfully implemented, right? So oftentimes as technologists, we think in a very, very focused way on our technical work, which is very important, but bringing in those other diverse voices and lenses really, really can help not only your innovation practice, but in a very practical way, making sure that your work can be successfully brought out into the world. I
So
see.
we,
Yeah,
we have a YouTube question. I think I can.
yeah, please. Great.
Gonzalo is asking how you recommend to acquire this perspective of facing new problems that are from, and areas that aren't your professional training.
Yeah.
How you can face that? How can I face, design, for example?
Yeah, that's a great question. I think, one of the really exciting things about today is now more than ever, I think it's easier to learn about new fields, more easily, right? Like new knowledge, new ways of getting insights, that barrier is a lot lower now, in part because of things like artificial intelligence, right? It's when I want to learn a new field, a new discipline, I think there's two parts, right? There's also, obviously, there's agent-based learning, which is now becoming more and more important and will become more important in the years to come. But I think another key bit of advice, when I want to learn something in a field that I don't know about, go straight to the top. Like, try to find the best people that are in that field and figure out how to work with them, how to ask questions from them, how to learn from them. I mean, this is something that's a little bit more privileged for me, as somebody that is a principal investigator and can teach classes and so on. But when I don't know something about a field, the first thing that I do is actually I teach a class about it. I will go and I'll organize a group of people that I can learn with, and go and invite speakers and people that are experts in that field, and then learn directly from those experts, right? You can spend, and I've seen this so often, like some of my great heroes and my role models are folks that are incredibly good at learning. And this is, I think, another part, I'm curious for the background of the folks here, but when I did my PhD at MIT, I would say the single most important thing that I learned at MIT during my PhD was actually not anything about synthetic biology or about microfluidics and gene synthesis. The most important thing that I learned was how to learn. Okay, I learned from myself how to teach myself new models, new concepts, right? When you're doing doctoral research and you have to create a new innovation, something new that's never before existed, all of a sudden you can't just read literature and read textbooks or whatever. You have to go and experiment and try things out for yourself and make a lot of mistakes, fail a lot. But in that process, you can build up a mental model for yourself about how to learn something. So I think that's really, really important, is learning how to learn, right? The more effective you are at learning how to learn, the more equipped you are to handle all of the different kind of innovation challenges, where now you have to learn very, very quickly many, many new ideas from many, many disciplines. So it's a very exciting time. And I think, I think, I really, I think if I were your age, it'd be a very, very important and exciting ways to, kind of explore all of these different ideas, all at once.
Yeah, I think, we encourage you all to reach out to those experts that you think that won't answer you, or that are super and impossible to reach, and they are usually super accessible.
They are.
they answer you. I mean, David is here, and David is super busy, but he took the time to join us and here in the other part of the world. So we encourage you to search for those experts. And Camila, yeah.
Yeah, actually, just very quickly,
Yeah.
I just want to re-emphasize, Marco, what you're saying. Email people, like just message them. I think, you know, there's a different feeling if you're an expert in a field and you're very, very busy. There's a difference, I think, between folks that are reaching out just from a genuine place of, hey, like, how can I learn? Is there a way to collaborate? I'd love to work together, etc. Those types of messages, you know, all of us started where you are, you know, like nobody gets any place alone, right? Like I always have had mentors and people that I also reached out to and emailed and asked questions for, and I still do to this day, right? I think, you know, one thing I'll mention in the remaining part of my talk, you know, leadership is important. All of you are seeking mentorship, but all of you are also leaders and mentors, right? There are people that look up to every single one of you, right? There are young people that are like, oh my be persistent, you know, show your excitement, your interest, go email people, ask people, figure out how to collaborate. You never know what doors will open for you unless you ask. You have to ask. You have to put that energy out into the universe, and then the universe will always conspire to help you if you show you know, that initiative and that enthusiasm and that excitement.
Great. Thank you so much, David. Camila, yeah.
Hello, David. Nice to meet you. I want to ask about the teams that you talked that are so diverse. How
Yeah.
do you identify that people that will help to your idea or your project?
Yeah.
I don't know how to search for those people, you know?
Yeah, that's a great question. So part of it, I think, depends on the types of problems that you're engaging with. So I'll give you one example. You know, I mentioned the coral project that I was working on. So one set of folks that was really important for that project were the technical biotechnologies, right? Folks actually doing real work with, you know, kind of probiotics and people working in that domain. But then there's also folks that are conservation scientists, right? People that are experts in, you know, coral nurseries and how to, you know, save coral and cultivate them and so on. You know, those folks are really important. But then also, you know, the community organizers are very important. The people that are actually thinking about how to engage with the various stakeholders that are in that region of the world. Like, let's say, you know, if this is for example, in Micronesia or another part of the world that's, you know, kind of engaged in coral conservation. So, and then designers for me in that project were also very, very important. We needed folks that could think about how to develop the different design tools to, in this case, we were doing a lot of work with engaging the community about the biotechnologies that were being developed. So design became very important for us. So I think, you know, as you're framing and thinking about your problem, and maybe I can ask you, Camila, what is your problem? Like, what's the area that you're working in right now?
My prompt is health. We're going to seek a project from longevity, you know, but I was thinking maybe it's not a doctor or a medicine investigator, which is the first thing that I think of, you know. Maybe it's not that person who I have to look for, you know. Maybe it's another one. Maybe you know, that's the first thing that came to my mind when you said that we need a diverse team. You know, we are all in the health team. We are all biology related people, you know, but maybe we need another vision here. Maybe where to go from a place which is not biology, you know.
Exactly. So that's a great example. So you're working in longevity, right? Longevity and health. So you would want, I think, at some level, having some kind of expertise with somebody that's got, you know, a medical background or can you know, kind of have some technical expertise in longevity. But, you know, again, there could be, if you're making a device or an interface or something that's about education and learning, you know, you could engage with a designer. If somebody's trying to make like a new wearable technology, if you're trying to engage with children or young people, right? So kind of depending on where you want to go, there's so many different types of experts that you could bring in that could be really exciting. And even, you know, folks like in computer science, right? Obviously, you know, artificial intelligence, there are all kinds of ways that AI could play a role in your project that might be surprising and interesting. Also artists, you know, there may be a big part of longevity could actually be around creativity and, you know, how do you actually increase meaning in your life? Actually, this is an interesting example. Later at the end of June, I'm actually speaking at a Buddhism and science event in Taiwan. And, you know, again, a big part of longevity is also around meaning, right? Purpose. Being able to live a purposeful life has been shown to be a really big indicator of long-term health. So maybe there's a spiritual expert on your team that is like there to think about, you know, how do we, you know, think about meaning in our lives, right? Or social connectivity, right? You might find somebody that's an expert in how to harness social connections later on in life. That's another big factor that connects to longevity. So longevity is a really interesting area where there's so many different people from a variety of different areas that could be a part of your innovation, right? So that's a great area. It's really exciting, actually. I'm sure you'll learn a lot in your project.
Thank you, David. Thank you so much.
Yes. Yeah, let's keep going.
Yeah, thank you so much, Cami, for asking. And Karina, you want to go next?
Sure. Hi, David. It's nice
Hi.
to meet you. So I'll be one of the mentors here in this batch, and the team from Nucleate have been kind enough to invite me to this session, which was very great. So touching on the diversity of the teams, I was wondering, because actually it happens to me every day. I come from a business background,
Yeah.
and I founded my own biotech company.
Oh, wow.
And my team is they're scientists and biotechnologists and biochemists and so forth. So we're working on producing palm oil without palm trees, lab-grown oils, so to speak, to prevent deforestation and all sorts of bad things on the environment. So I was wondering, David, do you have any tips on how to reach that common ground? Because I found in my experience that although not impossible, sometimes it can be difficult to find that common language, right? Where you can, like you said in your words, look at things from a different angle. And sometimes it's difficult to understand the angle the other person or the language the other person is talking to you in. So do you have any tips on that area?
Yeah. So when you maybe just say a little bit more, like when you're in your example, you know, you're making this palm oil kind of product. What is the challenge like, or who have you been trying to communicate with? Do you feel like that you've had a challenge kind of connecting with?
Well, first of all, our first challenge was the mindset, right? So I come from the business side, so I have like a business mindset, particularly related to startups, which is like a whole different beast. And my colleagues are used to working in the lab, so they work on the bench. And have no idea of business, and sometimes how fast a startup has to move forward. And especially, I think the main challenge is the lack of resources. Usually scientists work with, at least in Argentina, most scientists are scientists from a federal agency called CONICET. So the money is granted to them, right? Particularly grants, that's what they're called. So the money comes from the government, and they investigate with that money, and then when it's over, it's over. And in a company, it's different, right? You have to search for more money, or you have to be mindful of the budget, or so many aspects that are on the business side. So that's one of the challenges, right?
Yeah. So that is definitely a set of challenges. I mean, I think you know, in bringing together and trying to get folks from different backgrounds to understand, you know, your perspectives, obviously one of the best ways is through when you're actually working together on a project. You know, now, you know, if your scientists are now in this business environment and they're used to having to do stuff at a certain time scale, but now you're on a quarterly process where you actually need, certain types of results and so on. It's going to be a big learning experience for those scientists, of course, right? Now they've got to shift their mentality and they need to go do things in a new way. And it forces you to be uncomfortable. So here's another key thing. So I would say, diversity is important, but you also need team members that are also fast learners. That's really key. We've talked a bunch about that, but also people that are okay with discomfort, right? Like you have to be, if you're suddenly in used to doing things a certain way, and now, your business team is saying, hey, we need you actually to 10x and go faster. That might be very, very uncomfortable. And so I think you need to also find people for your teams that are okay with that discomfort, that are okay challenging themselves and pushing themselves in a new way, right? I would say the designers that I worked with, as an example, that CEOs of their own biotech companies, never been in a wet lab before, but they were very excited about being uncomfortable. They were very excited about being in a whole new field that they didn't know anything about, and saying, okay, I don't know what this is. And, Marco sees this, how to grow almost anything. It's such a great example. And I'll, in a minute, I'll take one more question, then I'll just very quickly wrap up my slides. But, how to grow, we have students that literally don't know the difference between a DNA molecule and a protein at the start of the class. And by the end of like 14, 15 weeks, it's really amazing. Like they're designing their own plasmids, their own new synthetic proteins. I mean, it's incredible. But they struggle. They really have to go through it. I mean, you see, Marco can attest to this. So many students, they're just like, man, there's parts where they really are very, very challenged. But what I find is the ones that truly flourish are the ones that embrace that challenge and then push through the challenge, right? And then on the other side, all of a sudden now you've got this designer that's got a new superpower, right? And so I think for the folks that are your scientists that might not know a business, now they're in it. They're going to have to really, really learn. And if they are willing to embrace that struggle and embrace that challenge, on the other side of it, they're not going to be business experts, right? They're going to be wet lab people that know, okay, for me to really be successful in a technical business environment, this is how I need to operate. This is the way that I need to learn. This is how I need to collaborate and work with my teammates, etc. Right? So I think that's another really, really critical attribute. Because if you're not willing to face that discomfort and push through the challenge, then you will struggle, right? Not every designer can learn synthetic biology and launch their own company, right? So it does take, I think, an ability to embrace that discomfort and that challenge, right? One more question.
Yeah.
Oh, go ahead.
Go ahead.
Yeah, I think there's one more hand raised. Is it Luz?
Yeah. Hi, David. Thank you for the presentation. It was very interesting. I'm interested in what you said about meeting people who are experts in the fields you are not, but also learning and getting yourself interested in that topic.
Yeah.
Where do you draw that line? How do you decide, well, up to this point, I'm going to learn it by myself, or where do I need someone else who is willing to teach me because I don't have the time or the resources to learn it all by myself?
Yeah. So there's this idea of kind of push versus pull learning, right? Like all of us have been in courses where you really don't want to be there. You have to take this class because there's some requirement or some other thing, and you're just sitting there and you have to regurgitate what the professor is telling you that you need to learn. And that I think is the least effective style of learning. The most effective, of course, is where now you're trying to figure out a problem. Like I'll give you an example. When I was doing my PhD work, I had a really wonderful mentor in synthetic biology that taught me about gene synthesis, but I didn't know anything about microfluidics. Okay, my advisor didn't know anything about microfluidics. Nobody in my lab knew anything about microfluidics. So I needed to go and teach myself that. So I literally found the best people on campus that knew stuff about microfluidics. I called them, I emailed them, I set up meetings, I went to their labs. They introduced me to a grad student that said, hey, you can follow this grad student, he can teach you some stuff. I did that. I found another expert, learned from them. So I really went out there and found and got as much resources as possible and folks to mentor me and help teach me in the thing that I really didn't know anything about, right? And then after a little while, I got enough kind of learning there, then I could start playing and experimenting my own. I started learning more quickly for myself. And I mentioned in my own doctoral work, right? The most important thing was not learning about microfluidics. It was learning how to teach myself something completely new that I didn't know anything about, right? And since that time, I've done that over and over and over again in my career, right? I got into collective intelligence, which is a field I didn't know anything about, but my colleague Tom Malone, he's the director of the collective intelligence center at MIT. I came to him and I said, hey, I'm a synthetic biologist. He didn't know anything about synthetic biology, and I said, hey, and I'll mention this in the slides the last slides I'm going to share. But we started building out this network of community biology labs all around the world. And I recognized that this was actually collective intelligence. These are actually people organizing these labs. We had this big global network of laboratories. And so there's a really exciting opportunity in collective intelligence connected to this network. And so I started teaching my colleague Tom about synthetic biology, and he taught me all about collective intelligence, and he was very excited because he said, oh, I can apply my ideas in collective intelligence to what you're doing in synthetic biology. And that made for a really exciting collaboration, because who's doing that, right? And it was a similar thing for me with community organizing, right? As we were building out this network of laboratories, really every single one of the folks leading one of these labs was a community organizer. They were trying to recruit people to come and join their lab. And there's decades and decades of practices around community organizing in the United States. And so one of my colleagues, Marshall Gans, he worked in the civil rights era in the United States. So you might have heard, Martin Luther King, Cesar Chavez, some of these very, very big figures that helped to create voting rights, for example, in the United States. All of that was done using community organizing practices. And I found Marshall and I invited him to the Bio Summit, like my big synthetic community biology conference. I've got this community organizer that's working with us. So again, all over and over and over again, finding people, experts that are in these very different fields and bringing them into synthetic biology and exploring, kind of new innovative ideas at that intersection. So I don't know if that helps answer that question, but, learn how to learn, try to teach yourself as much as you can, but then find those experts or people that want to collaborate with you and that you can learn from, and ideally working through a project. That's always the best idea. If you can get a project and collaborate together, I think that's one of the best vehicles to learn. Marco, I want to be mindful of time. I have a few more slides. Is there still time for me to talk for about another 10 minutes, or are we about time?
Of course, David, we don't want to take your time, but if you want to wrap up.
No. It's, for me, this is great. This is super fun. I'm really enjoying interacting with the community here. So maybe, Marco, what I can do is just 10 minutes, I'll wrap up, and then we can do some concluding questions, and then yeah.
I think we have a few more questions in the YouTube channel, but I think you can wrap up the slides, and then we can do some final questions.
Perfect. Yeah. I'll wrap up the slides, and Marco, keep track of the questions for me, and then we can do all the questions at the very end.
Perfect. Thank you, David.
Okay. Wonderful. Yeah, and thanks so much for the great questions. This is a really, really appreciate them all. Okay, so let me go back to the slides, and I'll finish here. Okay, so hopefully you're seeing the slides again, and let me go to the full screen. Okay, so again, the title of this talk is Innovation at the Edge, and hopefully I've been able to convince you the importance of many diverse creative voices, technical voices, and so on in your projects. And another big kind of set of ideas. This is a larger movement that a number of you may be aware of called community biology. So as people in the 2000s were launching the first kind of the synthetic biology laboratories, there were also people all around the world that were really excited about participating in biology, but did not have access to labs at MIT or Harvard or any of these other institutions. And they started setting up these community biology labs. And so in New York and in California, GenSpace and BioCurious, you may have heard of them, started organizing spaces in Europe. Some of the big kind of biohacker groups started getting together also in the early 20s and 2010s. And, this very much mirrored ideas from early computation. Again, I think you may be aware, this is Steve Jobs and Steve Wozniak, the two Steves that founded Apple Computer. And these guys were, again, building personal computers in their own garages. And so this idea of biotech and biology living in non-traditional spaces really has been evolving, I would say, over the past 10 to 20 years. People building biology labs in libraries, on buses. This is actually my colleague, Beno Juarez from Lima, Peru. He's been working for years on this floating biofab lab. The idea is for this lab that can float on the Amazon River and explore indigenous biotechnology. And so So this whole kind of global network I mentioned of folks setting up labs all around the world, and there's been folks throughout Latin America as well that have participated in community biology, have been a part of this event that I've organized for many years called the BioSummit. Some of you may have heard of the BioSummit. For over the years, I've had many, many colleagues from Latin America, Argentina have engaged with us in the BioSummit. And we've had 6 BioSummits now, starting from 2017. And so this is very much a community-centered event where we really are bringing so many diverse folks from all around the world and bringing them into the life sciences and biotech and synthetic biology. And over the years, we've worked with those groups to think about the ethics of our larger community, what our shared purpose is, governance, and so on. And a key thing I'll mention is leadership. I heard that mentioned in the opening remarks. And, all of you, I think, at Nucleate in your programs, all of you, I think, are you're innovators, but you're also exploring leadership at some level. And so we launched actually a community biology leadership program a number of years ago. We've had 3 cohorts of leaders. And there's a definition of leadership that I think is really important that I have found very valuable over the years. This is from my colleague, again, Marshall Gans. I mentioned he's at the Kennedy School at Harvard, but has been involved for more than 50, 60 years in community organizing practices in the United States. And his definition of leadership reads, leadership is accepting responsibility to create conditions that enable others to achieve shared purpose in the face of uncertainty, right? So we are, of course, living through incredibly uncertain times right now. Certainly in the United States, things are very, very chaotic. I think throughout the world, there's a lot of big challenges that we're all facing. Climate, biodiversity loss, global inequity, and so on. So a lot of uncertainty. And what I love about this definition of leadership is that leadership is a choice, right? Leadership isn't something that just happens on its own or that's an accident. It comes from each of us actually stepping up and embracing responsibility during a lot of confusion and uncertainty to really try to lead. But the other key part about this definition is around creating conditions that enable others to achieve shared purpose. So it's not about saying, oh, look at me, David Kong, and how special I am. It's about how do we enable people that are part of my team? It could be in my company. It could be in my community. How do we enable everybody that's a part of my group to be successful, right? And so that, I think, is a really, for me, as a community organizer as well, has been a definition of leadership that's been really resonant for me over the years. And I'll play you a little video. This is from members of our fellowship program from this Community Bio Fellows program, reading the statement of shared purpose that was co-designed at the BioSummit.
Hola.
Madame.
Jumbo.
Bonjour. Hi.
Hey.
Namaste.
Servus.
Vanakkam.
Привет.
Hey everyone. Hello.
Que bueno.
Our shared purpose
To fundamentally transform life sciences and democratize biotechnology,
to inspire
creativity, and improve life.
by organizing life science
Change makers and by enthusiasts to build an inclusive global network. Cultivate an accessible commons of knowledge
resources, launch community labs,
and projects and enable local educators.
to go out to the bang. Woo! I'm gonna play some synth music for you now.
So this is a really wonderful leadership team. Each year we've had 36 fellows that have participated, including some colleagues from Argentina you might have seen. And so over the years of the BioSummit, as we've been really thinking about bringing all of these folks from all around the world that may be a part of emerging bioeconomies, and thinking about how to both share their work. So we also have had a bio creation station for the artists and designers. We created a proceedings journal to help document all of the work that's happening at the BioSummit. And, a big part of my own background, I'm also a DJ. So, again, I think when you want to organize and build community, celebration is actually very, very important. At any type of organization, you need to be able to celebrate together as you work very, very hard together. So one of the very kind of most important ways, I think, for bringing in new voices and enabling greater creativity is through education and learning. And so I'll conclude by just sharing a bit about some of this work and also, again, how I know Marco. So at the Media Lab, we have this really rich tradition about taking technologies like, for example, coding, digital fabrication, developing a transformative learning experience. In the case of coding, some of you may be familiar with Scratch, which is developed by my colleague, Mitch Resnick. at the Media Lab. And Scratch has been scaled globally through what are called computer clubhouses. There are hundreds of these physical spaces around the world. And now over 100 million users have actually engaged with Scratch. And digital fabrication, my colleague Neil Gerchenfeld has taught a course called How to Make Almost Anything at the Media Lab at MIT, and has scaled that course globally through a network what are called Fab Labs. There's thousands of Fab Labs all around the world. Many of you may have be aware of some in Latin America or other places globally. And we've been doing something very similar with biology and the life sciences through How to Grow Almost Anything, which we've been scaling through this global network of community biology labs, and also what are called How to Grow Almost Anything nodes. And this past year, we actually had one of our nodes in Quito, Ecuador. And I know Marco and perhaps a number of you in the call have been connected to How to Grow Almost Anything as well. And so, this idea of a scalable learning network, having physical spaces where people can come and learn coding, digital fabrication, and now synthetic biology, I think has been one of the big exciting ideas that have come out of MIT over the years. And, again, I think when we think about learning, and, these are some ideas that might be valuable for you all at Nucleate as well, learning, we have this 4 Ps of learning, which comes from my colleague Mitch Resnick, this idea of passion, projects, peers, and play, right? That we work best and learn best in a peer-to-peer network where it's through relational learning. So again, the fact that you all are doing your projects and innovating together as in a peer group, I think is really exciting. This idea of meaningful projects is very, very important. I've done work over the years, again, with teams working, developing projects together. And those projects coming from a place of internal excitement, enthusiasm, very, very important for learning. And then, you get network effects. This is something that, as I think about the larger How to Grow network, I know Nucleate as well as a big global network, the ability to share best practices, resources, all of that's very important. And again, bringing in this idea of diversity and inclusion, very, very, kind of radical ideas that can come together and inform your own practice. And then this idea of meaning and purpose, right? When you're part of something, for example, like Nucleate, right? You're in Nucleate Argentina, but you're part of something that's bigger than yourself, right? You're now part of a national community and also a global community. So meaning and purpose also very, very important. So on to How to Grow Almost Anything, which again, I'm very, very proud of. Of course, I've been teaching now for many years with George Church, Joe Jacobson, and a number of faculty from all around the world, leading faculty in synthetic biology. And How to Grow is very much a hands-on learning course. So each week you learn a skill at the frontiers of synthetic biology and apply that in the laboratory. Some examples of some of the coursework. Of course, now with protein design and all of the applications in machine learning and artificial intelligence has been very, very exciting. The How to Grow Almost Anything students learn about AlphaFold, RF diffusion, some of these latest tools. We talked a little bit about genetic circuits, how to build more complex circuits that can be applied to a variety of applications, from metabolic engineering to making sensors and so on. We do work with cell-free systems, which are, for the artists and designers, are very exciting because you can freeze-dry those cell-free systems and apply them into textiles. You can also study the origins of life on Earth, minimal life. Genetic constructs as large as synthetic genomes are part of the course, and also automation and cloud biology. So this is actually a really important set of ideas. One thing that happened during the pandemic was students couldn't be in wet labs anymore, so we actually taught them how to program robots. And so I'll play a very quick video about the automation class.
How to Grow Almost Anything is an MIT, Harvard, and global synthetic biology class.
Each week, students learn a key skill in bioengineering, ranging from topics like protein design to cell-free systems, bioproduction, and CRISPR.
This week, students learned about lab automation with the Opentron's liquid handling robots. Students programmed the robot to dispense fluorescent E. coli bacteria into the shape of a design that they created.
After growing on black agar plates for 24 hours, the living artwork glowed under UV light. Here are some of the amazing designs that the students created.
If you're interested in learning more about synthetic biology, check out htgaa.org.
Okay, and these were some of the student designs. And so this is students programming Opentron's robots for art, but later on they did much more sophisticated work building genetic circuits in an application I'll talk about later called neuromorphic circuitry. So anyways, How to Grow has really grown dramatically over the years. This past year, more than doubling the number of accepted students, almost 1,300 students from all around the world. And again, an amazing group of TAs at MIT and Harvard, but also globally, with Marco and many other really talented innovators in synthetic biology. For me, I think one of the most exciting things about the course as well our TAs, the vast majority of the TAs were former students. So after taking the course, one of them, you kind of become absorbed into this big, larger global community. And then some of our TAs have also become faculty, which is a really neat part of the story as well. And again, the course concludes with the students presenting a personally meaningful projects. So over the years, we've had an incredible array of innovative projects. So Pat made this wearable for optogenetics to create molecules on the demand for space exploration. And this is Pat in 0G testing his wearable device. Yishao was a student from China who had never been in a biotechnology classroom before, had ever been in a wet lab, and then later became the CEO of our own biotech company selling desktop biology labs. AL's project on the DNA canvases became part of his PhD thesis, which he's wrapping up now. Belen was a management scientist, so she was somebody at the Sloan School at MIT, ended up designing whole cell COVID-19 biosensors. We have architecture students over the years that are thinking about ways to incorporate engineered organisms into the built environment. So again, so much creativity, right? As a synthetic biologist, I would never think about combining synthetic biology with architecture, but this is something that we see all the time in How to Grow Almost Anything. Again, designers looking at making biosensors out of chitin-like materials. This is Sophia's project from this past semester. Or making masks that could be infused with cell lysates to create pathogen detectors, or other types of systems for detecting cortisol in the skin, for example. Very low-tech modular biotech equipment. Again, more textiles incorporated with engineered organisms that are sensitive to temperature and pressure. Computationally designed enzymes for breaking down plastics. Spider silk spacesuits. I mean, so many incredible, innovative ideas from over the years on how to grow. I love this story from Andreas Rico. He's a city scientist. So he's a person that had, again, no expertise in synthetic biology, but loved building sensors in cities. And so he made an open source 3D printed bioreactor that could be used to cultivate cells that could be used as live cell biosensors. This turned into a big part of his master's thesis and a paper that we're working on publishing. And then students in the following year, Corinne, took that open source bioreactor and had used it to study microorganisms indigenous to Hawaii, where Corinne is from. And so I mentioned during the pandemic, students couldn't be in a wet lab anymore. So we taught them how to program robots. And this got us thinking about the future of learning in synthetic biology. And so this is one of our TAs, AL, working with one of the liquid handling robots. And we started to take our whole curriculum and figured out what parts could be done completely remotely. So this is the bioproduction lab where the students are engineering microorganisms to make a beta carotene or lycopene. And here they are programming the robots remotely. And so again, we started thinking about not just how to grow almost anything, but how to grow almost anything almost anywhere. Right, so with just an internet connection and a computer, you could start having access to this larger learning environment. And so we took our curriculum, figured out what parts were TA, could be done with TAs or with robots, or could be done in the lab or TA assisted, and started thinking again about this new model for global education. And we published this Nature Biotechnology paper. And again, I love the story. The vast majority of the authors are students, and many of the students had very little wet lab biology experience before taking the class. So again, imagine not knowing very, very little about biology, and all of a sudden you're a co-author on a Nature Biotech paper. And so for us, where we're going now with How to Grow Almost Anything is thinking about scale. How can we get folks all across Argentina, Latin America, engaging with synthetic biology, but with only an internet connection and a computer? And for me, I think this is a combination of both scalable learning networks, so both these physical labs all around the world, but also robotics. That's a huge, huge area of innovation. I think that is going to be a big part of the future of learning. And so, I mentioned, we have, these students all around the world, and now this growing network of How to Grow Almost Anything nodes. So this past year, we had nodes in New York and in San Francisco, in Quito, Ecuador, in Victoria and Ottawa, Canada, in London, in Seoul in South Korea, and also in Tokyo in Japan. And so you could take How to Grow Almost Anything in person at one of the nodes, or if you were in the same time zone, you could learn still with a cohort of learners within that node. So for us, that helped to preserve the peer-to-peer learning that I think is very, very important. And also, again, still engaging in the personally meaningful projects that are a big part of How to Grow. And so as we've been building out this network, we've been thinking, how can we all collaborate and work together? Many of you are likely familiar with iGEM, which is a competition amongst sites, but what if we could actually get everybody in the network collaborating and working together? And so last year we started a project on what's called phage therapy. So the students designed different bacteriophage, these lysis proteins. And so locally we had folks test those protein designs using digital microfluidics through a company called Nucleate. Nuclera, excuse me. And then now we're leveraging open source robotics and low cost robotics so that our nodes all around the world can try to prototype and test those same lysis proteins. And so this is an example of the digital microfluidics. So each one of these pixels is a different student protein design that's being synthesized using cell-free protein synthesis. And again, many of the student designs had a performance superior than the wild type, which was great. And now, again, we're leveraging this larger network to try and build and test throughout the world. And so this is a larger model, I think, where we've got, for example, supercore sites at a place like MIT with a lot of resources, microscopy, mass spec, and so on. But then this distributed network of nodes that have robotics, and we can share protocols across the network. We can share experimental data, and all of this becomes, I think, a really powerful infrastructure for global learning and innovation. I mentioned this year we're starting a project on, we started a project on what are called neuromorphic circuits. So these are genetic circuits. When you transfect them into a mammalian cell, they can behave a little bit like a neural network from computation. And so again, bringing this idea of computer science and synthetic biology together. And so the students designed their own neuromorphic circuits, programmed Opentron's robots to actually build those genetic circuits. And then this was students anywhere around the world could design and program the robot and design their own circuits. And then, TA at MIT ran the robotics and then did the data analysis. And so we've been thinking a lot about, as we scale this, how to also do biosecurity analysis of the protocols. And, for me, what's been really exciting is the continued growth of all this work, right? Now we're in this world where not just digital literacy is important, but also bioliteracy is important, right? How do we enable folks from all around the world to have some type of understanding of DNA and proteins? And just like, we take for granted now, internet literacy and digital literacy, I think in the years and decades to come will also biological literacy. So I'll conclude by just saying, we're working on this neat project now with Ginkgo Bioworks. We've been thinking a lot about cloud robotics and how to, again, how to grow almost anything, almost anywhere. And there's a paper from 1971. I've talked a bunch about computers in this talk, right? We talked about mainframe computers. And back in 1971, when the first, kind of major computer systems were becoming more popular, my colleague, kind of early founding director of founding faculty of the Media Lab, Seymour Papert, wrote a paper called 20 Things to Do with a Computer, right? So this is back before we knew that you could use computers for learning, creativity, biology, right? This is very, very kind of early thinking about computers. And now I think I'm very excited about this idea of 20 things to do with a cloud lab, right? As we push robotics, as we put automation into the future, there's going to be increasingly more opportunities for us to do creative work, learning, education. And so this is a set of work I'm really excited about. And this idea of combining learning networks, right? It's just like Nucleate is a learning network. How do we combine that with robotics to really increase accessibility and innovation for synthetic biology, not just for human life on Earth, but I think ultimately, one of my goals is planetary flourishing. How do we can live in greater harmony with all life forms on Earth? So I'll wrap up there. And again, we'll take some questions to wrap up, but please find me. I'm on social media at davidsuncom. You can find me on Instagram, Twitter, all the different platforms, and also on LinkedIn. So please connect with me there. I'd love to stay in touch. And again, thank you, Marco, so much again for inviting me and for taking the time to be here. So thanks so much again, everyone.
Let's give David a big round of applause. Thank you so much, David.
Thank you.
Was great. I love seeing people from Argentina with whom we presented a project in the Design Challenge.
Oh, great.
I think you know Heidi. She's so
yes,
great.
Of course.
Yeah.
Heidi is a dear friend. Yeah, I love Heidi so much.
Yeah, she's so great, and I think that if one possible thing came out of the COVID pandemic, it was being able to do this kind of things and connect all around the world. So thank you so much for joining us. And we have one question from the YouTube. That's
Emily.
Emily asked, how do you get people outside of your field involved in a science project? How do you find people who might be interested?
That's a great question. So I think so there's a number of different ways, right? Things like this are very important, right? You need to go where the people are, right? I'm sure, you know, it's over the years, so many people that I've collaborated with, I didn't know them before. I might have an opportunity to speak or share some ideas, like for example, even here with you all, right? If anything I've shared has moved you and you're very, very excited to collaborate, you know, reach out to me, right? Like you just never know how, you know, if you go to a talk and you're in an audience and you see somebody saying something that really resonates to you, go and find that person and go and connect with those people, right? This has happened to me. I've mentioned so many different times in my life, in my career, where I'm in the audience in a talk, or I see something online and I see a speaker and I'm like, wow, like what an incredible set of ideas. How do I reach out to that person? How do I go find them? How do I learn similar types of ideas from folks that are connected to them? And, you know, this is, I think, where a lot of your own perseverance is really important, right? We live in a world now where, you know, because of the internet, you know, it's so easy for us to actually connect and to engage with people from all around the world. So the ability to, you know, be persistent, you know, reach out, you know, go message them, you know, if any of you are excited about working with me, you know, send a message, you know, it's a big wide open world, and your own kind of activity is very, very important in fostering those types of connections. And also, you know, if you've got a platform for yourself where you can share your ideas, right? If there's places where you can, you know, publish your work, present your ideas, all of those are kind of ways of both learning but also sharing, right? Because getting your ideas about into the world about what you care about. You know, I'm guessing through all of your own projects, you're working in groups now, you're going to be doing some pitching and getting your own ideas out there. All of that's super important, and all of that's great practice as well. Like it's very, very you know, common for me to give talks and share a lot of my ideas, but that wasn't always the case, right? Everybody has to start someplace. So for when you've got your idea, go put it out there, you know, go start your own YouTube channel, go share your idea at a conference, you know, take a course like How to Grow Almost Anything. You know, that's a great way to develop a project and an idea, and all of a sudden you can share that publicly and with folks all around the world. This past year, we had like 13 hours of presentations from students all around the world. You know, it's so exciting to see all of these different ideas. So it's a big, big world and so many different opportunities. And the most important thing is your energy, right? If you've got energy, if you've got enthusiasm, anything is possible.
Thank you so much, David. I think, and I don't know if anyone has one last question, so we are mindful of David's time.
Hello. Yeah. 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 Are there specific types of biomaterials you mean? Are there you mentioned materials, right? Like the cement. Are there specific types of materials you're talking about? Yeah, 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 yeah. It's a great question. So, if you look, for example, in the field of like biomaterials and even biodesign, there are many ideas that are ahead of their time, right? You know, Suzanne Lee, she's an old dear friend, colleague. She gives the biodesign lecture on how to grow almost anything. You know, she has been making kombucha materials, all of these very, very innovative biomaterials, you know, more than 10, 15 years ago, right? And that idea wasn't quite ready at that time, right? She had the prototypes, but there wasn't an industry, there wasn't an ecosystem that could really support those ideas. So another part is timing is important. Time is actually very, very important. There are these really funny pictures from the Media Lab from the 1980s, right, of people making the first quote unquote wearable devices. It's a very famous photo of these like nerds with all of these crazy like glasses and things on their heads and so on. And it felt, almost ridiculous looking at these people and being like, what? Why would you be able to wear a computer? Like, that feels crazy. And now it's completely commonplace, right? All of us, we have like, I've got my wearables, like, all of us have very, very lower cost distributed computation systems that are a part of our lives, right? Ubiquitous computing, that felt like a totally foreign idea, in the 1980s and 90s, right? So timing is also important. But now I think as we look at kind of synthetic biology, biomaterials, and consumer products, there's so many more products that are part of our everyday lives, right? Almost for sure, all of us have consumed, some type of a bioengineering food, right? There's Impossible Foods, all of these other kind of lab-grown foods that are now becoming more common. And now also in fashion, for example, you've got mycelium materials, spider silk, all of these different kind of biologically grown materials that are now becoming a part of products. Now, I will say a lot of those biotech products are experiencing a lot of challenge right now. This is kind of a classic. You may have seen this sort of hype curve in technology, right? There's a lot of hype, and you see we're in the middle of that with AI right now, right? It's like, oh my God, synthetic biology is going to change the world. We're going to be able to do everything with synthetic biology. Oh my God, AI is going to change the world. We're going to do everything with AI. Lab on a chip is going to change the world. We're going to do everything with like, chip-based, laboratories, right? So there's always a big hype phase in any technology. And then there's a big, kind of the trough of disillusionment, right? Like you start trying and then, oh my God, things don't work and they're not as magical as we thought. And then there's kind of coming out of that low point into just the steady work of making something real and a big part of the world, right? And I think synthetic biology, we had our hype in like the past, 10 years, 20 years. There's also been a big dip, and then now there's kind of the steady work to come out. So I think to answer your question, we're now in a moment where I think there are, obviously in the health space, there's always going to be kind of easier ways to make innovations that are going to have widespread adoption, but increasingly consumer products are starting to emerge. Foods, flavors, fragrances, materials, that is starting to become more and more commonplace. And so finding your market is a really, really critical part, right? Who's going to buy your stuff? One last quick little anecdote, Ecovata, MicroWorks, these are companies making mycelium products. MicroWorks, I think, had a really interesting business model that's paying off for them. They've been collaborating, for example, with luxury brands, right? So going for very, very high margins where they could find, Hermes or, Louis Vuitton or whoever to make a mycelium bag, which would be very, very expensive, but could actually create, enough profit for them to continue their business. So that business model combined with a market opportunity, combined with an actual real product and a real biotechnology that's useful, all of that I think is helping them scale. Thank you for the question.
Okay. So David, thank you so much. This is
My
really
pleasure.
great.
My pleasure. Yeah.
I hope you had fun.
I did. This is awesome. Thank you so much. And yeah, please reach out to me, stay in touch. If you have questions in the future, we'd love to connect with you all.
We have two final questions. David, you have something?
Yeah. I have time.
The last 5 minutes? Okay,
yeah,
thank you.
Yeah, go for it.
Because I don't know, I got some delay with the raising hand. And yeah. And who wants to go next? I'm not seeing the raise hand.
Saw a couple hands. I just
Yeah, I saw like a few hands pop out.
What I think happened was they wanted to clap in the emotes, but they got confused, I think.
Okay, no worries.
Okay. Well, thank you, David. And
my pleasure. My pleasure. Yeah. And just
I hope you can join us. You can join us for the final pitch where the
I would
teams will be presenting. We will live stream that also. So
great. Yeah.
Invited.
Would love to come and again, just feel free to reach out to me. I'll mention in the chat again, but you can find me, David Sun Kong on LinkedIn and also here on social media. So yeah, send me a message. Please stay in touch and good luck. Very, very excited for all of you. Congratulations, Marco, on your great leadership on this initiative, and good luck, everyone. Stay in touch and keep innovating.
Thank you, David. Bye.
Thank you so much. Take care. Bye-bye.
Thanks, David. Bye-bye.
Bye-bye.
Bye, David.
Buenísimo. Para aquellos que nos quedaron en el YouTube, cortamos acá. Gracias por sumarse y